Hello and welcome to Lecture 8 of Introduction to Computational Literary Analysis. Today we're going to talk about type-token ratios, more about types, more about tokens, other things like that. Okay, here we go. So I'm going to open up a new notebook. I'm going to call this one Types, Tokens, etc. And I'm going to annotate this in Markdown and say that this is more on types and tokens. Okay, so again, imagine we have something that Porky the Pig says, that's all folks. And I'm just going to write this in Python. And if we were to split this up into words, that's what it looks like. We have 1, 2, 3, 4, 5 instances of the. So I can call this Porky words. I can do things like I can run Porky words.count on the, and it tells me I have 5 instances of it. If I were to do the same thing with all, of course it just tells me I have 1. So a type, in this case, would be the, and I can only have 1 of them, but a token for the, in this case I have 5 of them. Okay, so I'll introduce something here called a type-token ratio. So the type-token ratio is often called TTR, and it's just the number of types divided by the number of tokens. All right, so this is usually kind of like a proxy for the vocabulary of a text. However, one thing that's really important to mention is that it's very sensitive to the number of words in a text. So that means that if we're computing the type-token ratio of a number of text, we really have to make sure that we're comparing roughly the same amount of text in each. All right, so let's try this out. So if we have this Porky words thing, if we were to take the length of that string, this would be the number of tokens. Right? Maybe I can put that into a variable and call it the number of tokens. Now I'll introduce to you a new function called set. In set, it says it builds an unordered collection of unique elements. So if I were to run set on Porky words, you'll see that it comes up with all of the types. In other words, it doesn't repeat the because it recognizes that the is something that is just repeated in the list. So if I were to run, if I were to calculate the length of the set of Porky words, then this is the number of types. And the number of types here should give us 4, and the number of tokens should give us 8. So the type-token ratio is the number of types divided by the number of tokens. So in this case, of course, you probably guessed, it is 0.5. All right, so if we wanted, we could write this as a function too. I could say type-token ratio will take some kind of like list of words, let's say tokens, It will first calculate the number of tokens, which is just the length of that list of tokens. Then it will find the number of types, which is the length of the set of those tokens. And then it just returns the number of types divided by the number of tokens. So why don't we try this on some test texts. So I'm going to import all of the NLTK test texts from the book. And I'm going to do this right up here. And that's because it's often a good idea to put all of your import statements in the very first code cell. So this is a Python convention, but it's also a really good idea because it's good to open up a notebook and to see what the requirements of that notebook are, because maybe some of these imports come from a different library. So I'm going to say from nltk.book import star, and what this does again is just sort of loads all of these texts, and it does this thing where it assigns us to these variables for us, which is pretty handy. All right, so now we have all of these things, text 1, text 2, and they're already filled out for us. Texts, it shows us all of them. One thing that I can do is I can make a list of all of these if I want, and I could say text 1, text 2, text 3, text 4, text 5, text 8, and text 9 are all in this thing called all texts. And this is kind of handy because it just allows me to do something on everything repeatedly using a for loop. So I could say for text in all texts, print that text's name, and it prints the name of the text. I can also print the length of that text's tokens if I want to, and it tells me how many words are in each text. I can also do this thing where I could print the text's name. I could print I could do something like name and then padded with some white space, and then I could truncate this whole thing, slice this whole thing to like 25 characters or something, and then print out this padded version. All right, so I'm going to add some more spaces and truncate it a little less. And this doesn't do very much. It just kind of makes sure that I'm aligning everything on a certain column, and I can also add like a separator of some sort. Yeah, and then after this I could say now print for that text the length of that text's tokens. So now I have like a little table or something, so I could just read this a little bit easier. There are better ways of doing this in Python. You can use a format method. But we won't really go into that right now. So Moby Dick has 260,000 words. That's the biggest one. And The Man Who Was Thursday, a G.K. Chesterton novel, has 69,000. And The Personalist Corpus is the smallest with about 5,000 words. All right, so why don't we calculate the type token ratio for all of these? So I could say for each of these texts, print that text's name, and then print the type token ratio for that text. Okay, so it looks like the highest one here is the personalis corpus, but we actually know the personalis corpus to have a very low type token ratio. So what we're seeing here is really the influence of a very small number of words. So what we want to do instead is we want to compare the same number of words in each. So I can truncate all of these texts to, like a smaller number of words. The smallest I can go is about 4,800 words, because that's the size of the personalis corpus. So what I can do is say my truncated texts are right now an empty list, but I'm going to go through each text in my all texts list, and I'm going to say truncated texts. I'm going to append that text, but only up until append that text's tokens, but only up until like 4,000 tokens. So this is going to get me a truncated version of all of them. So truncated text, now if I look at this, it says it's a list, and it's a list of lists of 9. So it's a list of all of the tokens of all of these 9 texts. All right, so with these lists of tokens, I can now go through and calculate the type token ratio for each of them. But just as an aside, I want to point out that this is a very, very common pattern, and we're going to use this a lot. So it is good to talk about this for a second. So I'm creating a new list. I'm going through each item in an old list, and I'm doing something to that item, and then I'm appending that to my new list. Actually, to make this clearer, I could say truncated tokens is that text's tokens, but only the first 4,000 of them. And then I'm going to append that to my truncated texts list. So this is a very common pattern. You make a new list, you go through every item in an old list, and you build up this new list with items from the old list after you've done something to it. Okay, so there's another way of writing this that I could show you really quick. As an aside, a list comprehension is just kind of like a backwards way of writing a for loop. For the specific case of making a new list out of the results. So another way of writing the above is to write truncated texts equals text.tokens up until 4,000 for text in all texts. So this is the exact same thing as this, but we're just writing it in this kind of compressed format, in this format known as a list comprehension. So you can read it backwards if you want, and it sort of reads like a for loop. So I'm saying for each text in all texts, right, call that thing text. And then for that thing text, we want to get its tokens, and we want to get only the first 4,000 tokens. So now if we run truncated texts, we can look at it, and it should be a list that is 9 long, and each item in the list is a list of these tokens. So this, you can imagine that this is a really powerful thing, this list comprehension, because it allows us to do things like get the length of every item in a list. So if I get, the length of the text for each text in truncated texts, and if we just run that, then it tells us that each item has a length of 4,000. I can also do this thing where I could say lowercase truncated texts are, that text lowercase, or we could say, is that going to work? No, this is not going to work because it's not a string that we're dealing with now, it's the tokens. So we would have to do this differently. We would have to write a function, that would say like lowercase it, and it would take some list of tokens, and it would return, that token lowercase for each token in tokens. And then if we wanted to, we could say lowercase it for all of those tokens for each tokens in our truncated texts. And I shouldn't have actually printed this out, but lowercase truncated tokens. Now if we look at this again, this is 9 long, so it has each of our text in it, and it contains just the lowercase tokens for each. If we wanted, we could actually even go one step further and throw out punctuation, but this is good enough. So now we have lowercase truncated tokens for each of these 9 texts. So we have up here, our function that computes type token ratios. So now I can write a new list comprehension that just computes type token ratios for each of these texts. But these are actually lists of tokens. So I could say for tokens in lowercase truncated tokens, find the type token ratio of all of those. So now if I look at that, I should have a list of 9 type token ratios. This looks about right. So what I want to do now is just associate these with the names. So I could say, I could go through each of these and zip them together with all of their names if I want to, because now they're disassociated with their names. So one thing that I could do is say for I in range 0 to 10, print I. So this is going to give us, maybe I could say 0 to 9. This is going to go through each number from 0 to 9, not including 9. And I could also do this where I could say print the TTR value with that I index. So now it goes through each item in that type token ratio list. And now I have all texts and I could print out the name of alt text with that index. And I could print the type token ratio with that index. So you can see Moby Dick has a type token ratio, a very high type token ratio of 0.3. Jane Austen is a little bit lower. Book of Genesis is even lower. The Wall Street Journal, I think, is the highest of them all. So that kind of makes sense to me, because the Wall Street Journal news articles, they tend to have a very high vocabulary, not a whole lot of words repeating. So does Moby Dick. It's a very erudite novel with lots of very specialized vocabulary in it. I could have also written this in a different way. So there's a function called zip that can zip together two lists. So I could zip together a list of 1, 2, and 3 with another list of A, B, and C, and it gives us, it doesn't print it out. Maybe, I wonder what would happen if we tried to print it out, actually. This could be the kind of thing that we have to iterate over. It won't print it out for us. We can turn it into a list, I think. Yeah, I see I put the comma in the wrong place there. That's why it's doing that. Yeah, so what zip is doing here is it's combining the list 1, 2, 3 with the list A, B, and C, and it's doing it pairwise. So it's saying, now we have one list that contains the pair 1 and A, another one that contains the pair 2 and B, and another that contains the pair 3 and C. So this is a new data type called a tuple. And if I were to run the type on this, it would say it's a tuple. A tuple is kind of like a list, but it's immutable. So I could get the 0th element out of this tuple. I could get the first element out of that tuple, but I can't do something like append 1 to it, because it has no attribute append. So it's kind of like a list, but it's not really. So yeah, I can make a quick annotation about this. You might not see tuples a whole lot, but in case you see something in Python that is surrounded with parentheses, that's a tuple, and it's kind of list-like. So we've just zipped up 2 lists. So another way of writing this whole thing is, instead of iterating over this index, I could say, for text name and ratio in zip, and I'm going to zip together all of the texts and their type token ratios. I'm going to print those out. So yeah, now you can see it shows us the text and it shows us the associated type token ratio. I'm only showing you this to show you that there are just many, many ways of doing everything. Yet another way of, yeah, I mean, I could show you yet more ways of doing this, but it's, yeah, it's not necessary. Okay, so we've computed type token ratios. So we're computing the vocabulary for each of these texts. So we could also do this with, yeah, we could also do this with any other collection of text. So if we collect together, let's say, narratives from the Moonstone, we could compute type token ratios for those too. So let's do that really quick. All right. So first let's get the Moonstone. And on my system, it's in readings, content, texts, Moonstone. But of course, it's going to be different for your system. And then I can split it. So Moonstone parts is moonstone.split. I'm going to split on this double pound sign. And now we've already looked through some of these parts, and for example, we found that I think part 5 is the beginning of Betteridge's narrative. And actually just off screen, I've found all of these for us just to make things a little bit easier. So I've already found that Betteridge goes from 5 to 29. Here the Clack goes from 31 to 39, and Bruff goes from 40 to 43. So I've assigned these to variables just called Betteridge, Clack, and Bruff. But let's just verify Betteridge 0, is the beginning of the first period. And this is the very last bit of Betteridge. At the end it says the end of the first period. So so we know that this is Betteridge. It's always a good idea, by the way, it's always a good idea to check to make sure that the variables that you have are filled with the data that you expect them to be filled with. All right. However, if we look at some of the links of these things, we can see that each one of these is a chapter. And we don't necessarily want that. So maybe we want just the raw strings of each of these. So let's join them all together. I can use a list comprehension for this. I can write it the long way too. So I could say narrators is this new list. Write it the long way first. And say for a narrator in Betteridge, Clack, and Bruff, this list, take that narrator and join together that narrator's list using \n or line break, and we're going to assign this to a new variable, narrator string maybe, and then take narrators, this new list, and append our new narrator string. So essentially we're just joining everything together, and now this variable narrators, it should have 3 items, and each item is the string with that narration in it. Okay, so I'll show you the shorthand way of doing that whole thing, because we just learned list comprehensions. So I could say, instead of all of that, I could say, let's \n join together a narration for each narration in this list of Betteridge, Clack, and Bruff. And I gotta spell it right. Now, if you look at the list, it's basically the same list of all of these strings. And if I wanted, I could actually write a dictionary instead for each of these. So I could say something like narrators equals Betteridge is narrator 0. Clack is narrators 1, and Bruff is narrators 2. So I mean, that's just a different way of organizing this. So if I wanted to, I could say narrators Clack, and this would give me the full text of all of Miss Clack's narrative. Or I could print it out if I wanted. These are just different ways of accessing that information. I could also say narrators 1, and I know that this is Miss Clack, but it's Oh, yeah, that's right, because I renamed it. Yeah, so maybe I could name this something different, in fact. Yeah, so narrators 1 I know is Miss Clack. Yeah, it just depends on how you want to organize this data. So I recommend using something like a dictionary. You know, you can also write a dictionary comprehension. It's a lot like a list comprehension. But yeah, we won't really get into that right now. Because our main task is we've decided, yeah, we want to do a type token ratio calculation for each of these narrators. So to do that, we have to first get the number of tokens for each one, and then we have to get the number of types for each one. So we could do that all in one function if we wanted to. So we could rewrite our type token ratio function to just take a text string instead of taking tokens. And this could tokenize it first. And then get the number of tokens. And then we could get the types, which is just the set of those tokens. And then we could get the number of types, which is the length of types. And then we could return the type token ratio, which is the number of types divided by number of tokens. Okay, so that's one way to do it. And then if I know that this list called narrators is a list of 3 items where each item is a narrator, I could write, I'll write this the long way first and then the short way again. So I could write type token ratios is a blank list, and then for each item in narrators, for narrators, I'm going to compute the type token ratio, my new one for that narrator. And I could print it out if I wanted to. It says NLTK is not defined. So if you ever see something like this, and you know that NLTK is supposed to refer to the library, it's just a case that we haven't imported the library yet, so it doesn't know what NLTK refers to. So I have to go up here and import it among my import statements. So this is going to run everything again. So now if I come down here and run that again, it should work. Okay, now it printed type token ratios for each one of those. We could use my dictionary instead, and this way it'll give us labels that are a little bit easier to read. So I could say for narrator in narrator dictionary, what did I call that? Narrator's dictionary. Print that narrator, so that's going to be the key, and then print type token ratio of narrators indexed by narrators. So what this is going to do is get the value out of that dictionary, in other words, which is all of the tokens. So let me just write that out. Yeah, so it says Betteridge has a type token ratio of 0.07, Clack 0.12, and Bruff 0.17. But also, Bruff has the smallest, the shortest narrative of them all. So we do have to keep in mind that we're now comparing different amounts of text. So why don't we make a better function where we truncate this ahead of time? So one thing that we could do is we could bake in a function. We could write a new type token ratio that takes a dictionary of texts. Instead, why don't we annotate this with this thing called a docstring, which is just 3 quotes, and it's a little description of what our function does. So we could say this takes as input a dictionary where the dictionary keys are text labels and the dictionary values are a list of that text's tokens. And actually, you know what? This is just a string at this point, and the dictionary values are that text's string. All right, so we can do everything that we did before here. Actually, let me undo that. Yeah. So I have it in 2 places here. Yeah, maybe I can call this type token ratio dict, or maybe dict to type token ratio. Yeah, so it's often said that one of the only hard problems in computer science is naming things. And yeah, so naming a function as to what the function actually does is kind of tricky, actually. So it's going to take a dictionary of text where the dictionary keys are text labels and the dictionary values are that text string, and returns as output that dictionary again, but with type token ratios as values. Okay, so we got most of this. It's getting the tokens. Let's say that we compute the TTR. Actually, you know what? Because we've already defined type token ratio up here, we can get rid of most of this. We could say for text in text dict, TTR is type token ratio of that text. And then we can make a new dictionary called TTR dict. And we could add each one to it. So I could say TTR dict text equals TTR. So this will make the text, which is the text label. Actually, I'll call this text label just to make this clearer. And instead of returning that, I'm going to return TTR dict. So yeah, why don't we try this? Dict to type token ratio, and we're going to run it on our dictionary of narrators dict. Okay, a big error. Expected string or bytes like object. So it looks like word tokenize needs a string, but it's getting something other than a string. Oh, I think I see what's happening here. Yeah, so here we're trying to get the type token ratio of this thing called text, but we actually want to get the text itself out of the text dict using the text label as key. So this is the text itself, and then we want to get the type token ratio out of it. Kind of debugging in real time here. Great. So it says that Betteridge has a type token ratio of 0.07, Clack of 0.12, and Bruff of 0.17. So this kind of makes sense to me because Bruff, is a solicitor, and he kind of has a high vocabulary that he uses, maybe, excessively high vocabulary. Miss Clack has a slightly lower vocabulary, and Betteridge has the lowest vocabulary of all. This kind of makes sense to me intuitively, just based on having read the book. Yeah, anyway, we could have done this a number of different ways. We could have run a for loop over each of these things, so we have this thing, narrators. We have this value, and it's just a list of 3 items, and those items are each strings, so we could run this function, which takes a text string and returns the type token ratios, and we could do it this way. But if it requires a little bit more programming, but if we use a dictionary to keep track of the label for each text, then we can get a lot more mileage out of it. Okay, so next I'm going to show you how to count words. And in a sense, this is something that you already know how to do because we know how to count something in a list, right? So we already have this list, porky words, which is just the, that's all, folks. And we know we can count this list, count the number of these in it. So that's really all there is to it for counting something. So if we have this dictionary, this narrator's dictionary, let's see what we have here. Narrator's dictionary Clack gives us the full text of Miss Clack. Yeah, what I want instead is tokens. Now, do I already have that somewhere? Yeah, so I have this thing called lowercase truncated tokens from before. Yeah, maybe I could start with that instead. Oh, yeah, that's right, because that's all of the test texts. Yeah, why don't we do some of that with our narrator's dictionary. Uh-oh, I'm printing out the whole thing. Yeah, I don't want to do that because it's taking up a huge amount of space. So first I'm going to lowercase all of the words there, and then I'm going to remove some of the punctuation optionally. Yeah, so for each of these narrators, I'm going to make a new container for this. And then I'm going to say for each narrator in this narrator's dictionary, the narrator, I'm going to call it, maybe this is narrator label. narrator's dict narrator label, we know that this is the narrator text itself. Okay, so we can take that narrator text and lowercase it. And if we want, we could write something to replace some of that stuff. So we could replace the star with nothing. Or we could write a for loop. We could say for punctuation mark in, and then we could give it a whole list of things. We have to remember to reassign it here because strings are not mutable. And we're going to replace that punctuation mark with a space for now, just to maintain whatever that is doing semantically. So now, this is removing the punctuation. And then we're going to take our clean text and then create a new dictionary with that label, and we're going to give it the new text. So let's see what that did. That's a bad idea to print it all out at the same time. But it did lowercase it. It did remove the punctuation. Well, most of the punctuation. So I can actually take this and copy it and paste it there. I'm going to copy that and paste it here too. Add a few more of these. Yeah, it's kind of getting better. Yeah, I can keep adding these things. Yeah, this is kind of like a funny looking apostrophe. I can add that one. And in fact, that sort of thing sort of belongs in a new function, so I can make a new function called like remove punctuation. And then for some text, I could say for all of these punctuation marks, clean text is that same text, but we're going to replace that punctuation with a space. And of course, I have to start by initializing Actually, we can just operate on the text itself. So then that works iteratively. Yeah, always a good idea to test a function. So remove punctuation. Hello, world. Yep, it replaces it with spaces, which is actually what we want. It doesn't matter if there are too many spaces here, I don't think. So now instead of this whole thing, we could say lower text equals lower text, but we're going to remove punctuation on that. This should actually be up here, I think, to make things easier. This should be up here too. Now let's look at that again. Yeah, it's a pretty clean text. So you'll notice that this thing 2, this little code is Unicode for a non-breaking space. So if I were to copy this and paste it here, I wonder if that will do the same thing. Okay, yeah, it's pretty clean now. So we've just cleaned up the text, and now we want to count the words in each one. So I could do that with a dictionary comprehension if I want. Let me do it the long way first. So I could say tokens, my tokens dictionary is something new, and I'm going to go through each narrator label in this narrator's dictionary. But actually I'm going to go through the clean texts dictionary, and the clean text is that clean texts indexed by my narrator label. And then tokens are nltk.word tokenize that clean text. And now I can add this to my tokens dict using that narrator label as the index. And now if I look at this tokens dict, yeah, you can see it's just a list of tokens that have been lowercased. Punctuation has been removed, and we have a dictionary of it. So because it's a dictionary, it's really handy, and we can do lots of things with it. So yeah, we wanted to count words in things. So tokens dict Betteridge is going to get me all of Betteridge's tokens. I can even call them Betteridge tokens if I want. I could say how many are there? There are about 80,000 words. I could do the same thing with Miss Clack. I could say how many tokens are there? There are about 30,000 words there. And you know, because it's just a list, I can do things like I can count a word, like I can count him. You know, I could do tokens dict Clack count him as well. And I could write a little function, just a little tiny function to compare word counts if I wanted to. So I could take some word and I could go through each item for, yeah, so this would be like for narrator label in my tokens dictionary. I want to get the tokens out of it, and then I can count the number of times that word appears among those tokens. But I should print this. I should print this out, and I should print it out with the narrator label. So let's compare word counts for, say, like the word him. So it occurs 400 times in Betteridge, 133 times in Clack, 63 times for Bruff. Okay, so you know that doesn't really tell us very much because Betteridge actually has way more words than any of the other narrators. So we could change this function a little bit to adjust for the number of words in each. You know, so we could say, don't just give us the raw count, but divide that by the length of the tokens for that narrator. And now you can see that the one that uses the word him the most is Gruff. You know, what about her? Here, Miss Clack uses the word her more than anyone else. What about Godfrey? And here, notice I had to put this in lowercase because we're dealing with lowercase words. So Miss Clack sort of unsurprisingly uses the word Godfrey way more than anyone else. Yeah, I'll show you kind of like a sneak peek of what we're going to do later in this course, which is use pandas. Pandas is this data analysis platform. If we import it using this incantation, import pandas as PD, you know, then I can actually bring this into a pandas series, and I can plot the result as a bar chart. Really, well, yeah, sometimes that would work. Except for here, yeah, I don't want to print this out in that case. Yeah, I want to create a new dictionary for it. Yeah, so yeah, I would have to adjust this a little bit. So word count dictionary. It's a new dictionary, and instead of printing this out, I'm going to add this to my new word count dictionary. I'm going to return it here. Yeah, so it's going to be the same thing, but it's going to be a dictionary instead. And now that it's a dictionary, I can make this into a pandas series. I'm going to assign that to some variable called Godfrey's. And I can plot it as a bar chart. And it shows me that, you know, this is just the same data as this. It's just kind of neat to be able to see it as a bar chart, because you could just sort of see at a glance that Miss Clack uses the word Godfrey much more than anyone else, you know, by like a factor of 4 or 5. So if we wanted to, we could actually abstract this a little bit more. Compare word counts. So now we could just try any word in here we wanted to. We could even put an input in there. You know, so what word do you want to compare? Now let's try Rachel. It says Rachel is used actually way more by Miss Clack. That kind of surprises me. Let's try this again. What word do you want to compare diamond? Betteridge uses it the most, followed by Gruff. Miss Clack doesn't seem too interested in this diamond. Yeah, what other words should we compare? What about Crusoe? So Betteridge is the only one that uses Robinson Crusoe among these 3 narrators. So this is pretty fun, isn't it? You know, because we really just created kind of like a one-line program. If we wanted, yeah, we can make that a little bit easier to read by saying first take the input and then yeah, we could call this counts dictionary, or yeah, just counts. And we're going to compare the word counts of that word. And then we make a pandas series of the counts. This is way easier to read and much more explicit. And I can say that's a series, and then at the very end I'm going to take that series and plot it as a bar chart. So Godfrey, let me just make sure this works. Yeah, what else? What else could we do? Think? Mr. Bruff uses the word think way more. What about past tense, thought? Miss Clack uses the word thought way more. Okay, so this is fun, comparing word counts, word frequencies like this. Yeah, there are just one or two other things that I wanted to show you before the homework. And another thing is like sentence tokenization. So we already talked about NLTK word tokenize, and you know what this does is break a text up into words. So yeah, I'm gonna actually write this in Markdown. So NLTK word tokenize breaks up a text into words. NLTK sent tokenize breaks up a text into sentences. So remember, we have a dictionary of all of these texts, like way back here. I think it's called Narrator's Dict. Yep, so Narrator's Dict Clack will give us all of Miss Clack's narrative. So I can make a list of Clack sentences just by running NLTK word actually sent tokenize on her narrative. Actually, let me make this even more explicit, you know, just by putting this down here. And putting it into a couple of variables. So yeah, let's look at a few. I'm just going to pick a random number like 47. So this is a sentence from Miss Clack's narrative. Is it written by a man or a woman, miss? Let's pick sentence number 84. I've fallen insensibly into my Sunday school style. Miss Clack is really hilarious. Most appropriate in such a record as this. You know, and if we want to get the length of a sentence in tokens, you know, we could get Clack sentence number 85 and get the length, and this is going to tell us it's 44 characters long. You know, we could also get the number of words there by doing NLTK word tokenize on that sentence if we wanted to. You know, and then we have it broken up into words, and we could get the number of words by taking the length of that whole thing. It's 9 words long. So yeah, one of the homework assignments is going to be to get the average length in words of all of the sentences in the narrative, in each of the narratives. And so this will get you pretty far with that. Okay, but I should go back and talk about a few other ways to count words. So we've compared word counts here just by using dot count, or the count method, on a list of tokens. But you know, let's say we want to get big level statistics about counting words. So back to counting words, I'm going to show you a few other tricks. So like, let's say we want to just count all the words that Betteridge uses. So we already have narrator's dict Betteridge. And so we could call this Betteridge tokens. And now let's just do a sanity check where we check to see how many tokens there are. Yeah, he has 431,000 words. Is that right? No, that's way too many. Yeah, that's because it's a string and not tokens. Okay, so yeah, let's tokenize this. And now we have 94,000 words. Okay, that makes way more sense. Good thing we checked. All right, so to count all of these words, we could do it the long way. So the long way is by doing something like this. So we first start a dictionary, and we're going to make a dictionary that looks like this, where you have a word as the key, and then the value is the number of times that key occurs, right? So, or the word and its count, the number of times it occurs. So to make this, we're going to go through each word in this Betteridge tokens, and we're going to add it to this count dictionary, basically. So first we want to see, is that word already in there? Yeah, so we can say if the word is already in Betteridge counts, then we're going to take that count and we're going to increment it by 1, you know? So we could say Betteridge counts word plus 1. Otherwise, it's not already in the dictionary, so we're going to add it. And we're going to assign it like an initial value of 1. So let's look at what we have so far. Yeah, great. So we have all of the words. However, they're not lowercase, and we still have punctuation in here. Yeah, that's fine. Anyway, so this is the long way of doing it. So I'm going to annotate this by saying the long way of doing it. And now if we were to do this the short way, it would look more like this. So to do it the short way, I first have to import this library called collections. And collections is a library that comes with Python, and it has this neat object called counter. And counter is kind of like a dictionary, and it can count things. So if I run collections.counter on Betteridge tokens, which is a list, I can call this Betteridge counter. And now let's look at that. It's basically done that whole thing. It's done this whole thing for us. So that's really neat. We could treat it the same way we would treat this dictionary. So we could say, all right, well, show me how many times the word diamond with a capital D occurs. And it tells us that he uses it 148 times. But I can also say other things, like, say I have this counter. I could also say, show me the most common 20 words in Betteridge. And these are the most common 20 words with the number of times they occur. Of course, you know, it's treating punctuation as words. Sometimes this is useful though, right? Because sometimes we're interested in how many times punctuation occurs. So yeah, why don't we see, for example, how many times punctuation occurs? Well, that might be a homework assignment. Like, how many times does a quotation mark occur actually? So let's not do that right now. Anyway, the counter object is like a really great way of doing this in shorthand. So we can make this a little bit better if we wanted to, by before making Betteridge tokens, we could take our text, so narrators dict Betteridge. Yeah, we could lowercase this, and then we could remove punctuation. Yep, and then we could word tokenize that. And we could call it like Betteridge clean tokens. Let's see what that looks like. Let's only look at the first 100 or so. Great, yeah, that's very clean. And now if we were to run the counter object on that, so collections counter, make a new counter for bet clean tokens. Great. Yeah, and now if we wanted to, we could look at the most common, say like 30 of these. And this tells us that Betteridge uses the 4,000 times, my 1,000 times, etc. Yeah. So if we wanted, we could make a counter function for this. Make counter, and it would take some kind of text, and it would return that text lowercased and tokenized and everything, and we would also want to run the counter object from collections on it. So yeah, this is the old way of doing that. So yeah, why don't we run that on narrators dict clack, and this is a counter of Miss Clack's words. Yeah, and now that we can do something like this, we could actually do that for all of them. So we could say counters is a new dictionary, and we could say for narrator label and narrator dict, narrator label, this is actually the text, and then the counter is going to be make counter of that text, and then I'm going to add it to that counters dictionary with the narrator label as the key. So something is not working. Yeah, narrators dict. Yeah, and now I have this, I have counters for each of them. So now I could do the same sort of thing if I were interested in comparing the word diamond and how often it's used. I could say for narrator and counters, the counter is counters narrator. So print narrator and counter for, let's say, him. Occurs 400 times in Betteridge, 133 times in Clack. Counter for diamond. Great, yeah, so these are, just lots of different ways of counting words. And we're going to get into even more sophisticated ways of counting words relatively soon. Oh, I'm getting a phone call. I'll be right back. Okay, well, that's it, actually. Yeah, and we're going to get into more sophisticated ways of counting words and manipulating those counts pretty soon. Great. So have a good weekend, everyone, and see you soon on Zulip.